It's so exciting to be here. We welcome you all to our session on observability at scale with monitoring as code. Before we start, let's take a quick poll. Raise hands if you have a self-servicing concept enabled in your observability setup. Great. Raise hands if you have a tracing backend that you have tested for at least 10 to 20K spans per second. Very few. Raise hands if you're actually listening. Oh, that gets the right baseline. Okay, wonderful. So for those who haven't raised hands, not to worry. We sincerely believe we have something to showcase. There is something that you can take home today from what we are going to show from this discussion. And for those, some of you who have raised hands, maybe we are in the same boat. We have taken a different route, or maybe something for you to understand from what we have experienced. So let's see how things goes. Let's start. My name is Vipin, and I am with Amway Global Services for the last 3 years. I work for Global SRE team, and I am based out in Singapore. And here is my colleague Sai, please.
Hi, I'm Saiabhinay. I'm working for Amway Global from last 3 years as a SRE engineer, and I'm based out of Tokyo. Thanks.
Nice. So we'll start with a small introduction to our company, Amway. Some of you may already know Amway. It's a health and well-being focused company based out in US and globally operating in around 100 plus countries. And last year, as we speak, the revenue was around $7.4 billion. And we are mainly into supporting entrepreneurs, almost around 15 million entrepreneurs plus we are supporting, primarily in the form of direct selling. And we are primarily known as the #1 leader in the direct selling market. With that, let's start to our specific agendas. Nothing much fancy there, but our goal is to take you through some of the journey that we had in Amway, especially when we were doing one of the recent projects, which we call as NextGen. So it was an ambitious project that Amway was investing time for the last 1 or 2 years. And we would like to discuss some of those specific observability requirements, especially in the area which is tracing metrics space. We will discuss about the observability platform architecture. We will discuss about some of the components that we have actually picked here. Finally, we will also have a small demo about how observability with monitoring as code is implemented and how it is actually running in our environment. And towards the end, we will also touch base on a couple of challenges, some interesting challenges that we have faced, and how did we address them. So let's begin with some of those goals in the tracing and metric space. If I simply put it this way, the requirement was like this. We were looking for an observability as platform model that is capable of having a self-serviced management, especially for the application team users or the developers, so that they can get onboarded without a need of a platform team or an SRE person. At the same time, it was also demanding a single pane of glass observability, which consolidates the visibility of all the deployments that we have across globe. Now, if you put this in a quantified manner, what we are talking here is primarily on the metric side. We have hundreds of clusters running across globe in different markets wherever Amway operates. And it is about thousands of nodes when you put together, and maybe around 3,000 plus containers in each of the environments that we have. And per environment, we have around 130 plus microservices. And all of these are running on Istio service multi-cluster mode. So that again attributes to a lot of complexities on the metrics side, right? Some of you may be familiar in that. Now, the metric story doesn't end there. There was also an ask to include the cloud infrastructure metrics as well, which means something like whatever that we provision in our cloud, which is primarily AWS, like ALB, Lambda, and so on. All those metrics were also expected to be covered within this visualization. Now, these metrics were expected to be part of alerting. Some focused on KX-based alerting, some focused on infrastructure-based alerting. Moving on to the traces, the expectation, this is a bit interesting. 100% sampling was expected from the entry point of service mesh to the exit, which means any transaction that hits our service mesh, it was expected to be covered by the traces till the time it goes out. And it is not just a service mesh, the applications were also expected to be part of the tracing solution. And another interesting point, asynchronous events or the Kafka were also expected to be part of the tracing. So this all attributed to the sizing complexities that we had on our tracing backend. And we believe we have done something there, which we will showcase in the upcoming slides. Now, before we jump into the architecture components of observability, we'll start with a small introduction or a high-level introduction to the project that we are working on, which we call as NextGen. We hope or we believe that with this understanding, it will be easy for us to get connected to further understand, as we discuss in the slides, about the components what we have chosen. Now, for NextGen, if I put it this way, it was an architecture that got evolved over time within Amway to have a consistency across all the deployments that we are doing across globe. Which means anything and everything with respect to code development will start in this highlighted portion, which we call as global development or a centralized development environment, where once validated, these codes will be automatically pushed via our CI/CD pipelines to each of those market regions. So the markets or regions, whatever you see here, you may relate it as maybe market region one is India, the second one is US, the third one is Korea, and so on, and whatever that in future may come. At the core of each of these entities where these deployments are done, they look the same, basically. They only vary by the size and the numbers or the configs, but otherwise they are the same. What we are talking here is a couple of services, maybe around 130 plus services, split it in a 3-tier model, app, biz, data. And they are all running on an Istio multi-cluster setup with EKS platform as the base infrastructure. Now, it's very easy to put it this way. We wanted a strong platform so as to orchestrate all these component complexities, right? And that's where our platform, which we call as NextGen platform, comes into picture. Here, as you may see, it's actually something that we have defined on top of AWS services infrastructure. Now, for us, it's not just the infrastructure. For us, this is a set of standards and principles that we have defined and codified into AWS CDK L3 constructs. I'm not sure how many of you are familiar with CDK L3 constructs, but it's something similar to Terraform or IAC in the exclusive to AWS space. So it's a 100% GitOps model. So anything that an application team wants to get provision or on a day-to-day basis they want to get things done, they basically consume these constructs, what we have defined, maybe directly or through our own platform tools that we have in the platform, say Backstage, for example. So this way, they get things done as and when they want it. At the same time, they maintain their boundaries of what they can do and what they cannot do. Right? To get you further seriousness about what this platform is, we also have our own custom CLI, which we call as NextGen CLI, which is something that is purposely built to do an orchestration of all the component CI/CD in our architecture which is across globe. And finally, like any other platform, we also have lots of platform tools, developer tools, observability tools, and where CNCF has a significant presence. And here we are trying to represent some of those, which really powers our platform. We'll not go in detail, but let me touch some of them based on their contributions or their involvement in the observability space. For example, Istio is one of the major contributors in both spaces, both metrics as well as traces. Argo CD is also a contributor to metrics. At the same time, at times we use tracing as well. Then coming to other portion of tracing, Strimsy, Kafka Connect, these things are also a big time contributor for the tracing workloads. We also have use cases of Envoy gRPC, where we extend our service mesh to capabilities like external proc. And we expect the tracing and metrics to cover these. So with that, I believe we now have some foundation about what exactly are we working on, and we will now jump into the observability architecture, what we have actually defined. And here we go. It's a simplified representation. Basically, what we are talking here is two pieces of things. One, we wanted a centralized monitoring for which we have a central monitoring account. You may consider it as an AWS account, if it helps. And then we have all those tenant deployments. It could be any business initiatives or any of the deployment which we have across the globe, who would like to send or store their observability pieces, for example, the K8s metrics, infra resources metrics, and tracings. So now coming into the monitoring account, what we have done here is we have, again, a piece of construct which we call ourselves as Observability CDK construct, which is, again, a custom thing which helps us to completely define the observability infrastructure, starting from its prerequisites to storages and its networking configurations and so on. So coming to the other pieces of our architecture, starting from metrics. When it comes to K8s metrics, we have Grafana remote write agents, which basically scrapes the metrics from these sources and then push it into our central monitoring account, which is an exclusive storage for the K8s metrics. In fact, the largest one. And coming to the infrastructure metrics, where we talk about ALB, Lambda, and so on, we have CloudWatch exporters who basically do the job of converting these CloudWatch metrics into Prometheus compatible one. And finally, for a persistence, we get it stored onto another Prometheus compatible storage, which is nothing but an AWS AMP, which is exclusive to non-K8s metric space. Moving on to the other part of the architecture, which is OTel, the tracing. We have OpenTelemetry collectors that runs in each of these deployments, whose job is to basically receive all these traces that is getting generated from our sources, any of the workloads, any of the components that we have in our architecture, then ship them into our backend tracing solution, which is Grafana Tempo. And finally, it gets stored into the backend storage, which is nothing but an S3. And all these pieces that we are seeing here, tracer storage, metric storage, and metric storage for non-K8s, everything goes natively attached to our visualization layer, which is, again, Grafana. In fact, that was one of the main reasons for us to choose Grafana Tempo over other tracing solutions, because it had two advantages. One, it was natively getting attached to the Grafana front end, and at the same time, it was offering us some other PromQL-like capabilities. If you may know, Grafana Tempo has a language called TraceQL, which is something similar to PromQL. And the same visualization layer, Grafana, is also helping us in the form of alerting. So all the metrics that we are talking here, the Grafana is also helping us to set up alerts as in when we need. And the last piece within our architecture, which is also an important one, which is monitoring as code as a construct, which basically enables the self-servicing that we were talking about earlier. And we will be discussing about this in the upcoming slides. If you look at these components, Grafana agents for the metrics or for the metric storage with CloudWatch exporters, they are somewhat straightforward. So we thought in this limited time, we will take you through some details about how exactly our OTel integration is done, because there are a couple of interesting pieces there which you may find attractive. So here we will try to represent how our traces are getting collected from each of these workload sources, how they are shipped, and how they are finally getting stored into our central monitoring account. We'll start with one of the simplest building block, which is nothing but a node. And this node has a couple of pods and containers, like any other node that we know, right? And in our case, we also have a significant presence of Istio in the form of several proxies that we have. Now the question is, how are we getting the tracing enabled for this, right? So here comes the OTel instrumentation. And how we are achieving it? We have our own OTel framework artifacts that we have published using code artifacts or in the form of boilerplates, which are working along with the applications so that they get instrumented well. And not only that, there are a couple of environment vars that gets along into this instrumentation, which also tells the instrumentation where to send these traces and what are the attributes that you can use yourself to enrich your metadata. So those we achieve using our own microservice Helm chart. So once this is done, our applications are in a way ready to start sending out traces. Now comes the question, who is actually receiving these traces, right? So we have several choices there. You could have possibly send these traces directly to the backend solution that we have, or you could have possibly deployed OTel collector as a single deployment within your tenant. Or there is another possibility, you could use a sidecar model of deployment. Or there is another possibility, you could use a daemon set model. So among all these choices, what we preferred over others is the daemon set model, because we felt it is offering us a low latency, at the same time less operational overhead, and also less resource management. So with all these put together, we decided to go with, as you see here, we deployed it as an OTel daemon set. In simple words, what we are saying here is, it's a collector that is running locally on every node that we have in our architecture, whose job is to exclusively deal with these components, get their traces, and ship them into our central account. Istio also does the same thing, but we don't have to give any framework to it. As some of you may know already, Istio comes with its own native extension provider for this OTel integration, and we just hook that with some of the configurations. Simple as that. So once these data are collected, the traces are collected, we securely transport them using the TLS encryption, which is front-ended by a network load balancer in our central monitoring account, who will pass it on to a couple of OTel receivers whose job is to do the first level of processing and then identify the right targets of tempo and then eventually pass it to the tempo for the last processing. And finally, this data gets stored into an S3 bucket. Like I said, this S3, about Grafana Tempo earlier, about the TraceQL advantage, native integration, this S3 was another piece which also favored us in our decision about tracing backend. It gives us a lot of flexibility in terms of scaling concerns and even the cost as well. And finally, let me also add this point that with all this, what we just discussed, we have tested, or we have seen our test cases hitting a span rate of at least about 80K spans per second today. And with that, I'm concluding my topics. I'll hand it over to my colleague Sai. Thank you.
Thanks, Vipin. First, setting up the context on next-gen and observability platforms. Let me now walk you through how we built monitoring as code, or MAC, into our platform. So our goal was very simple. Want to onboard observability seamless for developers. That means no tickets, no waiting on SREs, or no manual Grafana edits. What you see on the screen here is a sample microservice repository. Every repository has a folder called monitoring as code. And that's our way of storing observability configs. Inside this config folder, we have configs for on-call alerts, alerts for infra, services, and dashboard configuration. These configs were picked up by our AWS code pipeline and then invokes our L3 CDK construct called AMS Grafana resource. So here, the AWS code pipeline is unique for every microservice or microservice repository we have. And the CDK L3 construct, what we built, is an abstraction on AWS CDK. We wrote in TypeScript, and Grafana Terraform provider, and some source logic for environment level renderings. This CDK construct not only provisions, alerts, on-call configurations, and dashboards, but also validates the config before a deployment triggers. The pipeline runs into two stages. First, we deploy to pre-prod environment and then to production. So we follow the standard GitOps model, same like application code. Everything you see here is version controlled, peer-reviewed, auditable, just like application code. On the end, the output lands here. All the Grafana dashboards are automatically deployed. Alerts are configured along with on-call infra, and everything is tied right to teams by config. This enables us a true self-service capabilities in observability. Teams can evolve their alerts, dashboards, on-call configs, escalation policies, everything by code. And it's fast, reliable, and tightly integrated with CI/CD flows. Now, let me show you how this looks like in action. So here you see a sample microservice repository where we have a monitoring as code folder. This also has some CDK app which invokes our CDK L3 construct, what we have defined. And we also have a folder called configs, which holds all our alerts, dashboards, and on-call configurations. Each of these folders has market level stacks. That means we have various markets. Let's say market 1 and market 2 are our deployment entities. And each of these markets will hold environment level configurations. So we're talking about some service level alerts, what we have configured. You can see as a sample, we have an HTTP client high latency error with an evaluation window of 80 seconds and with a routing key. And teams define their own escalation policy for individual routing keys. We can also see some of our sample dashboards, what we have here. Few of the dashboards can be inherited right from the platform, or teams have the freedom to define their own dashboards as per the need. And these dashboards are in the format of Grafana dashboards in the JSON structure. And here are some of our on-call configurations. Now, let's move on to our AWS code pipeline. As we referred earlier, the code pipeline is unique for its individual microservices. So we have various stages. It validates the stack. It deploys the common infra, which might be on-call infrastructure. And then the deployment goes to pre-prod and followed by production. It is just like any GitOps model. And these are some of our alerts, which we have configured. And these are just the translations what we have on the repository from YAMLs to here. And these are our sample dashboard, what we have configured in the JSON structure in the repositories. And here we are just talking about the cache hit rate and miss rate. This is something specific to individual services. Apart from this, we also have a lot of common dashboards, what we have ranging from AWS Infra, Istio Ingress, Egress, and some of the Kafka and asynchronous dashboards. Here are some of the sample Kafka dashboards, what we have in this platform. Not just here, we also have some of the dashboards which relates to release and pipeline metrics, which we cater the information directly from AWS as our source. This gives us the visibility on the microservice level, pipeline deployment rates, release rates, and all the DORA metrics, what we need. In the end, monitoring as code just doesn't give us the visibility on app metrics, but also the complete infra components and pipeline and release metrics. Now, let's move on through some of our challenges and lessons we learned. Like any system running at scale, we had our own share of surprises. Let me walk you through 3 key lessons we learned the hard way. First, going with metrics. We had series of intermittent incidents where the metrics were almost doubled. Ingestion rates, active series, everything was doubled. And that caused our metrics dropped or skipped at Amazon Managed Prometheus, and also overwhelmed our Grafana agent pods to crash. On further analysis, what we found, why this behavior in the platform. So there were several batch jobs running at very regular frequency, few even at 1-minute interval, which generates short-lived metrics and high cardinality metrics. Our strategy for this was to convert any batch jobs which are running with less than 15 minutes of interval into a microservice, which would emit an aggregated metrics. By following the strategy, we stabilized our active series and ingestion rates, and also were safer on the AMP quota for service limits. Going on to the next challenge, what we had was on traces. So I can say this is in a unique case where someone is using Grafana Tempos in a multi-tenancy mode. In our case, spans from different environments were overlapping. So we started troubleshooting on isolating these spans. Then what we have noticed is this is an issue or a bug coming from the Grafana Tempo gossip ring membership logic. Tempo ingesters from different environment are accidentally forming a shared ring because there was no environment level isolation being recognized into it. So we reached out to Grafana community and raised a first public issue of such behavior. And further, we worked with the community and fixed the upstream Helm chart to introduce a instance identifier. After the fix, the Grafana Tempo ingesters were able to isolate their gossip rings by these identifiers. So from then on, we never saw our spans are overlapping across multi-tenancies. That brings us to the next challenge. Again, we have on traces. Here, we're talking about the trace context lost on CDC flows. Let me explain you about the problem and the solution we have tackled on the CDC flows. As we scaled observability, we also started looking deeper on its trace visibility, not just in asynchronous flows, but also on end-to-end CDC pipelines. In our architecture, we have microservice calls going to DB, and then a Debezium connector from a self-hosted Kafka connect pushes the data to a Kafka topic, and then that consumes by our downstream consumers. We are able to trace from microservice to DB, but then the trace just disappears, since there is no linkage between Debezium, Kafka connect, or beyond. We are losing the trace context midway, which made impossible for us to visualize the complete journey of a transaction. How did we solve this problem? We had two-step process here again. We built a custom OpenTelemetry interceptor, which is written in Java, and we baked it into our Kafka Connect base image. And we also started adding our trace parent into database columns. So how does this interceptor and trace parent help us to solve this? The component what we built called custom interceptor, which reads the trace parent coming from the DB payload, then moves into Debezium connector, which gets injected into our Kafka message header. If the trace parent is valid, it reconstructs the parent span and then attaches a child span. If the trace parent is malformed or missing, as a fallback strategy, it generates a new trace parent. This gave us a trace continuity, right from microservice to DB, Debian connector, Kafka Connect, and even our downstream services. We have applied this pattern for multiple pipelines, and it helped close a major visibility gap into our platform. So what does this leave us today? Now, our observability platform supports over 16 billion metric points per day with an injection rate of 200K per second. We have over 12,000 active alerts configured into the platform and 300 Grafana dashboards. And we have a consistent trace spans of 5,000 seconds per second and peaks up to 40,000 K spans per second. And we also tested our span capability. We could scale up to 80K spans per second. And we have over 100 plus monitoring at code pipeline runs every month. All this feeds into a single centralized Grafana, what we call a single pane of glass, which covers over 100 plus EKS clusters across global markets. Developers can onboard observability by default. They can still customize all they do, define and deploy through code. We have saved thousands of hours in ops, thanks for the automation and developer empowerment. That's all from us. Thank you. Reach out to us on LinkedIn. We'll take if you have any questions. We did not increase the limits. Our metrics were already filtered out to maintain that limits. Yeah. We have segregated our AMPs into a specific way where our application metrics are going into a separate AMP and CloudWatch and other metrics are going to a different AMP. And we already sized our enrollment metrics in a way that we filtered out unnecessary metrics. So we were never expecting that a sudden surge should happen because the active series should remain same. We were heavily into AWS cloud platform, so that was our quick win when we started. Yeah. Yeah.
When you have the option of declaring all these alerts and dashboards as a config map, sync it directly through the RMS, what made you to use it via pipeline? If you look at our ecosystem, almost everything is done via orchestrated via pipeline. So we wanted to maintain that exact same visibility for the users. So bringing another platform will sort of, Follow question. Yeah. So are you storing all these dashboards and all that in one single repo, or is it coming from the application repos? All 130 plus repos, all 100 repos.
So the application has
Its own set of repos. They have their own folders where these will be attached to. Yeah. Good question. Actually, it's 14 days. 14 days. Actually, that itself is too much. In our experience, we feel that maybe 3 days itself is good enough. But for these days, there are a lot of beta testing and all going on. So hence, we are leaving it for 14 days. But over time, we will sort of bring it down to 3 days. Yeah, it's a common problem with everyone, right? Because there are too many of them. So, and if you think of respecting all of them and storing them, that will consume your metric data points, eventually cost and complexities. So, what we did was that initially we started without any blacklist, complete expose of all the metrics. So then over time, as we matured, we noticed how many metrics are actually being used by dashboards. So then we ran a filter through, and then we found out, okay, these are the metrics which are actually actively in use. So then we roll out the blacklist plan, and then, yeah. Yeah, it's a long process. Yes, yes, yes. But if I may add, for example, Istio, there are some documentations where it says that these are the so and so metrics which are ideal for environment. Yes, yes, we do have. Yeah, we also have AppDex, yeah, all sort of SLO combinations as well. Yeah, yeah. Yeah. So obviously the cost, scalability, we don't have to worry actually, right? If somebody is ready to offer storing it in S3, what else we want? I mean, for us, the biggest problem was that how are we going to deal with the latencies with S3, right? Because S3 is, after all, it's an object storage. And from a user experience point of view, when they put a trace, how fast things are going to get fetched. That's what ultimately the concern is, right? And we don't really care where it is actually getting stored, isn't it? So what we noticed is that in Grafana Tempo, they use a backend format called Apache Packwit, and it basically does a very good deal about how they are managing the caching and storing of it. So that way, we found out it to be very niche in terms of user experience. So that was the reason.